Hello, my name is Sophie Lee, and today I'll be presenting on the work that I did this summer, which are Monte Carlo simulations of electron and phonon thermalization at the diffusive ballistic crossover point. I did my work with Raj Kati, Michael Rooks, and Stefan Najperj. And I was generously supported by the Robert L. Blankenberg SURF Fellowship. So to begin with, let me give you some context for the simulations that I ran. The group that I worked with has developed a detector that is able to measure temperature differences up to the accuracy of a single photon. So a single photon is incident on the flake over here. And in our case, this flake is a graphene flake. The graphene flake causes the incident photon causes a temperature change on the graphene flake, and this changes the resonance frequency of the resonating circuit over here. And we can measure that resonating peak, which is shown over here. All of these peaks are different resonating peaks at different temperatures. So with decreasing temperature, we see an increase in the resonance frequency. And so with that, one can measure very, very distinct temperature differences. As one might imagine, because of the accuracy of the detector, it's very important to exactly know what kind of temperature changes are actually happening on the graphene flake. And that was the main idea of my SURF project. It was to better understand the factors and impacting the temperature distribution on a graphene flake in the micron scale. And the way we approached this problem was by performing ray tracing Monte Carlo simulations on ballistic phonons and electrons. So Monte Carlo simulations are simulations in which one assigns probabilities to each collision, to different factors within the simulation. So in our case, this was for collisions between carriers, in this case, phonons and electrons, and the boundary. And then through repeated random sampling of these probabilities, one can then have a better idea of the full physical system. Furthermore, we have to distinguish between two main carrier regimes, one being the diffusive regime, in which the dimensions of whatever sample you're looking at are much bigger than the mean free path. The mean free path is the average distance that a particle will travel before it collides with another particle. And so in the diffusive regime, it's much more likely that a particle will collide with another one before it collides with the boundary. However, in the ballistic regime, L is much smaller than lambda, which means a particle is much more likely to collide with the boundary before, making it much more important within the simulations. Because our detector is at a very low temperature and we're looking at very small dimensions, we fall within the ballistic regime for now. And that's why our Monte Carlo simulations were initially just ballistic phonon and electron simulations. So we wanted to be able to verify our results with existing literature. And in this case, we then heavily used the algorithm that was presented in Tom Klitzner's paper, Phonon Radiative Heat Transfer and Surface Scattering. Klitzner did experiments on polished crystals of very pure silicon, and he combined these with 3D Monte Carlo phonon simulations. And with that, with the combination of these two methods, he was able to quantify the effect that different factors have on the behavior of the temperature at these crystal boundaries. Our simulations were quite similar. However, one of the distinct changes we did was move from 3D to 2D because graphene is a 2D material. And also, we also included the movement of electrons within the boundary because we also have to account for these within a graphene structure because it has a huge impact on the thermalization. So I'm first going to give you an idea into the main processes that we did within the Monte Carlo algorithm for phonons. And after that, we'll look at the results for the phonons and then look at the changes that we made for the electron Monte Carlo algorithm. So to begin with, we set up a boundary, as we can see here. And then the simulation started when a random point along the source is chosen, which is the point of origin. And then we also assign a direction to this point. The direction is chosen randomly, so that's one of the probabilities that we're looking at, and it's chosen from a cosine distribution. So that's in accordance with Lambert's law. And with a direction and a position, we can then calculate the trajectory of this electron with this of this phonon, and then calculate the closest point of intersection with the boundary. Um, and from there, we then have a choice to make yet again. Yet again, the probability comes into play. And we have this parameter f, which is the probability of diffusive scattering. So with probability f, we have that diffusive generation of the direction according to Lambert's law, which then generates a random angle regardless of the angle that it came in at. However, with probability 1 minus f, we have a deterministic specular reflection. So the angle of incidence is equal to the angle of reflection. Then we can again calculate the trajectory. Here in this image, we see that the particle has now collided with what we call the thermometer. And at the thermometer, the probability of diffusive scattering is a little different. It's characterized as the emissivity of the thermometer. So with parameter epsilon, we have absorption and re-emission. And again, the particle is absorbed and then emitted from a random point on the contact with Lambert's law. With probability 1 minus epsilon, we have the specular reflection again. Eventually, the particle is absorbed into the drain. However, we can also have backscattering at any point across this, and the particle can then be reabsorbed by the source. And that's very important when we look at the results later on. Here are some of the resulting trajectories that we have for different kinds of boundaries. And we do want to be able to put our simulations into the actual context of an experiment. So we want to be able to convert what we have into temperatures. And we do that by first assigning each phonon with a specific amount of power. And then because we know in a lab what the heater power is, for instance, we can then use Lambert's law to, we can then use Stefan Boltzmann to change that the heater power into a temperature, and then normalize it against the number of electrons that are released from the heater. And with that normalization, we can then also determine the temperature at an arbitrary point along the boundary of the flake. And the results that we have are shown here. These are one of the very first results with a very simple boundary. A boundary just like this, where we just have a source and a drain on the other end. And we see that with increasing probabilities of diffusive scattering, so that parameter f that we were talking about, we have a much higher chance, a much less chance that the particle will actually make it to the end of the end of the channel. So the likelihood of backscattering is much higher with higher Fs, such that the phonons are absorbed back into the source. We can also compare our results to those of Klitzner, and we see that both of the plots are very similar, and that's one of the first indications we had that our results were, that our simulation was in fact working as it should be. Yeah, so now we can move into the second part of the second part of the verification, which was against the simulations that Klitzner did to compare to his experimental results. So we set up boundaries to look exactly like the crystals that Klitzner used over here. And they have a source, they have some kind of thermometers over here on these two edges, and then we also have a drain. We have large thermometers as well as small thermometers. And this is what the temperature profiles look like. So here's the temperature on the side here, and here's the boundary. And we can see some of the most important aspects of this plot are the temperature drops. These happen exactly where the thermometers lie, and that's because at the thermometers, there is a higher chance of backscattering. So the particle is less likely to be able to get past these thermometer points. And that causes the temperature to actually drop after those. And we see that the scattering is very significant when we have large thermometers, and the temperature drops are nearly the same as an entire length of the regular boundary. And when we compare our plots to Klitzner's, we can see the overall profile shape is extremely similar, and we also see that the temperature drop due to the heater is well reflected. There is slightly different normalization. However, overall, the what we see is that the phonon simulations are in complete support of Klitzner simulations, and therefore we can safely use these phonon simulations in ongoing work. However, we also wanted to look at the electron Monte Carlo simulations because electrons have such a significant impact on the thermalization in graphene. And unlike in the phonon case, where we could simply use a um, billiard-like model, we actually have to make some quasi-quantum mechanical considerations for the 2D electron gas. And the way that we started our simulation was by looking at a toy model with the boundary over here, which was also done by Rukas in 1992 with his paper on transfer resistances. So we use that as a starting point. Um, in an electron gas, um, the momentum vectors can form a Fermi circle. So in our case, a 2D circle in which, and when you have zero temperature, all of these momentum vectors lie on the circle that is at the distance of the Fermi energy. So in this case, it would be 10. And we start with a equilibrium Fermi circle. So this blue one is centered at 0, which means that there is a 0 net momentum. However, under some kind of force, for instance, a voltage, the equilibrium Fermi circle is shifted. In K-space, this means just a horizontal shift, but it actually means that there's a net momentum of the electron gas in the forward direction. And we then input this non-equilibrium momentum distribution into our simulation here, where each electron that we run through the simulation is assigned with a k vector from the distribution. And what happens is that in addition to the phonon simulation that we were looking at before, with each a collision, something happens to the k vector. So with probability f, diffusive scattering, we have a randomization of the k vector, and with specular scattering, we have a reflection of this k vector. And when it collides with the voltage contact, we have the same thing, just with a different probability epsilon. And what can happen is that all the k vectors, if you only have diffusive scattering, all of the k vectors will eventually, so the green ones, the finals, will all lie on this blue circle here underneath the green circle. However, when there's only specular reflections, none of them will actually return to the equilibrium point. And when there's some kind of probability between 0 and 1, we have that some k vectors will lie on the equilibrium circle and some of them will not. So these are the three, this hopefully gives you an idea of what we're looking for. We're looking for how many of the k vectors will end up lying on this equilibrium circle, and that's what we've plotted here. So here's the ratio of the k vectors centered on the Fermi circle, on the centered Fermi circle, and then on the x-axis is the distance from the source. And we see that over the course of the boundary, the for the electron k vector distribution relaxes back to the equilibrium distribution, and this is exactly what Rooks also expected in his analysis. Now, this is a very preliminary plot, so we have a lot of work to do in terms of also um, being able to convert the temperature, the results we have from the k vector into an actual temperature distribution. So that's something that we will be doing in the future. So in conclusion, we were able to make phonon Monte Carlo simulations that fully support existing literature. And then we were also able to make the preliminary steps for electron Monte Carlo simulations. These also begin to support the existing literature. And with these two simulations going, we can then also create finite temperatures for the electron Monte Carlo simulation such that it can be coupled with the phonon Monte Carlo simulation with some kind of coupling constant. And then we can have a full Monte Carlo simulation. And through various additional features put into this Monte Carlo simulation, we will be able to fully understand the temperature distribution of the graphene flake better. So we can have better idea of how the single photon detector works at very accurate scales. So I'd like to acknowledge Raj, Michael, and Stefan for their help throughout the course of the summer, and Robert L. Blankenberg for his financial support. Finally, I'd like to thank the Student Faculty Office for their organization and commitment to the SURF program. I'd also like to thank you for taking the time to watch my presentation. I hope to see you at the Q&A session. Thank you very much.